Welcome. In this session in linear data analysis, we'll explore the logic that underlies the Perceptron Rule, which is a rule in machine learning for learning how to separate data. Here we're going to assume that we have a hyperplane that we want to use to separate set 1 from not set 1 data, and we'll represent this as the augmented weight vector W. We'll have an observation that we represent as an augmented vector light object, and we've augmented this with a 1 to correspond to the augmented weight vector. The label that comes in is yi, and let's observe that that is either a 0 or a 1. Now, let's explore the 4 conditions that could happen for our data. Suppose that we have a proposed W. This could come from a user. We could have selected it randomly. We may have an algorithm that tells us how to get an initial estimate of a W. Now, let's suppose that what we have is this. Let's think of the logic. So let's think of, suppose that the label is 1, and when we perform our computation of x transpose W and we run it through the Heaviside function, we get our quantization. Suppose that our quantization is 1. Well, if that's true, then what we have is, what action do we want to take? Well, I would think that what we want to do is, if we've correctly classified that data, what do we want to do to our hyperplane? Well, I think we don't want to do anything to our hyperplane. So I'll represent that action as we will keep this. And let's call this the case. So what case is this? Well, this is a true positive. That is, we have labeled the data, we have classified the data as 1, the data have a label as 1, and so what we have is a true positive, and in a true positive we don't want to do anything. Well, what about a true negative? That would look like our label of the data is 0, and our classification of the data is 0. And likewise, I wouldn't want to do anything to my estimate of the hyperplane because it seems to me that it's doing a perfectly fine job where it is. So that is a true negative. Now, what do we do if, let's say that the label of our data is 1 and the classification is 0? And the question is, well, what is that? Well, this is a false negative, right? Because we've classified this as negative. It's actually positive. So that is a false negative. What do I want to do in this case? Well, what I want to do is I want to move the hyperplane. If it is classified it as being a 0, then that means my hyperplane is too far in the negative direction. So what we want to do, and this is the key to the perceptron algorithm, is let's add the transposed data-like, vector-like data. And what that will do is that will move our augmented weight vector a little in this direction so that we're trying to get this from being a negative towards being a positive. And then the remaining case that we have here is our label is 0 and our classification is 1, and that would be a false positive. And when this happens, when the data are actually on the negative side of our supposed hyperplane, but we're saying it's on the positive side, that means that our hyperplane is too far towards the positive direction. And what we want to do is we want to move that slightly in the negative direction. Now, I've left a space here, and the reason is that we can actually concisely state this. There are a lot of tricks that we use in machine learning and data analytics, and one of them is taking advantage of the coding of our data. Here we've coded this as 0, 1, and here we've coded the classification as 0, 1. So what we can do is we could form the error. And now we can ask, what is the error? And what we'll say is that the error is the label minus the classification. So let's note that. We will say that the error in I, we will define that as being the label minus the classification. And the error here is 0. So let's write EI equals 0. And here the error is 0. Here our error is 1, and here our error is minus 1. And now what we can do is we can match these error values with the action. What are we doing when the error is 0? We're leaving this as unchanged. What are we doing when the error is plus 1? We're adding our data to the augmented weight vector that represents the hyperplane. What do we do when the error is minus 1? We're subtracting it. So what we can do is we could say this. We could iterate for all I, and what we could do is we could say that our new estimate of the hyperplane gets our previous estimate of the hyperplane plus the error for this data, for this observation, times the augmented vector for this observation. And so we're able to go from the logic that we have through the action. We can tie that to the 4 cases that come out of a confusion matrix or contingency table, and we can relate that to the error that we have, the error being the difference between the label and the classification. So this algorithm, this update method, now gives us a way that we can implement the perceptron rule.